So in the last video, yep, part two, I cut it off rather abruptly. I was just talking about the memory model of inside the EVM, and you just have to conserve memory. So sometimes you may have to split some of the Fyrd things into more than one function. So we're just showing you how to do that here, mainly because the second Fyrd script, it's it's taking all those values. There's six arrays of 350 points, and it has to eventually convert those all to strings, and to concatenate it into one giant path string that gets put in a path statement. So that one does use quite a bit of memory. So yeah, that's kind of where I ended the last one, and now I'll continue from there. So if I scroll back up to lines 50 to 53 is where we're calling the the Fyrd scripts. So the pound sign operator, that's telling it call a Fyrd script. The first number is the index. There's two Fyrd scripts, so we're calling index 0 and then index 1. And then the second number is we have a special return area it's an array of areas that you can put return values from Fyrd functions. I think there's 16 of them. So when you call a Fyrd function, you can tell it basically which slot you want to put the return values, whatever they are, in. So here we're calling the index 0, the first Fyrd function. We're telling it to put the return value in this special return area, slot 0. So, and then the second call on line 51 is doing the same thing. It's calling index 1, which is the second Fyrd function, and then it's telling it to put the return values there. But it also has to, you can also pass in a slot that you had from one of these previous calls, like on line 50. And there's another primitive, I think it's called, I can't remember off the top of my head, pound sign. I think it's just pound sign. Maybe it might be a greater than sign. But that's just telling it, that's just saying which slot you want to use as the initial parameters, and it defaults to 0. So like after line 50, we could have called that primitive and put a 0 in it, which means pass in this return value 0 that we got from the first function call. I mean, it would mean pass those values into the second call, which is on line 51. I know some of this looks pretty cryptic, but when you're executing things on chain, you have to be really careful with memory, especially when it's large arrays, and you can't copy things multiple times, because every time, whenever you allocate memory, it never gets released inside the EVM. So you have to be very careful about your memory usage. So that's why we have these sort of fixed areas, and maybe some of this looks a little bit cryptic, but it makes sense when you understand how the EVM works. Yeah, actually that primitive, I think it's pound sign greater than, because you can see we're using the pound sign less than function on line 52 here, and that one that's used to extract some of the return values. So that's what that function is doing. So let's look at the second Fyrd function, which is starting on line 117, and this is really just taking all that floating point data that we generated, and it's converting it to two giant strings that are going to be used in path statements inside SVG. So on line 117, we have this special exclamation point J operator, and it's setting the arity for the join function. APL doesn't have everything is either unary or like monadic and dyadic, but we wanted to have a join function that you could use any number of parameters on the left, like that's if you look at line 124. So we had to add this special arity operator to tell it. You have to tell it how many joins you want to use. It defaults to just to one, or yeah, I think one. So yeah, that's why that's there. And if you look at lines 118 through 123, these are just the pound sign S exclamation point. That's converting that array to strings, and the 2 is the number of decimal places that you want. So it's each one of these arrays is 350 points, and so each of these statements is converting. And the exclamation point, when you see that, it normally means in place. So we have an area that holds the number that we use, the int 128. But then inside that same slot or variable, there's a place to put an array of strings, and so we're just converting those to strings and putting them in the same variable. So on line 124, we're just taking those 3 points and making them into a single string, which is an SVG line. And then 125, we're just extracting 20 of those lines. That's what we're going to use for the hair highlight. And then if you look at line 126 and 127, it's using the pound sign J operator, which is the join operator, but it has this special modifier, this // that's called the reduce modifier. And modifiers in APL and in Fyrd, they modify the whatever the primitive to the left of them is, and it generally does the right thing, what you would think it would do. So, you know, if this were a plus sign, then what it's going to return is just going to add up all the values. So for this case, the join is just going to join all the values in those arrays into one string. So M and P contain just one large string. The first one's much larger. It's 350 of these lines that you see right here concatenated together, and then P is just a smaller version of that, and then that's what it's returning to Gyve. So now if we go back up to the Gyve function, we can see that this line 52 and 53, they're getting those 2 string values. They're saying that this pound sign less than operator is saying from slot 1, which is returned in line 51, get the first value, and it gets a string value by default. There's ways you can get array values too. There's another operator for that. But so after these execute, M is going to have a long, that's going to have a long path string, and M and P are going to have path strings in them, SVG path strings. So now if we go back, if we look at the rest of what's happening here, line 57 through 70, we have all our values, and now we want to generate the SVG for our image. So that's done via this, if you see this double greater than primitive, that's called a stream primitive. A stream is an array of strings. So the first parameter that you see to the stream primitives, like on line 57, 0, that's just saying set the first string in this stream to whatever this value is following. So, and there's actually one other stream. I don't have to talk about that one now, but this is the one that will generate the image stream, the double greater than. And the reason that there's an array of strings is that it's related to memory. We have to concatenate this giant, it's going to be a fairly large payload when it's done, and it all has to be concatenated into one string, and then it actually has to get converted to base 64. And this is all done on chain, so because of the memory model, you have to be careful about how you allocate memory, and you don't want to be copying strings more than once if you don't have to, because each time you just have to reallocate a buffer and recopy it. So when we get this array of strings, in this case there's 0 through 13. This is generating our SVG. We just have to concatenate. We have to allocate one buffer, and then copy all of these all these strings to that buffer to generate the SVG. So it's just it's the most efficient way of doing it. So here you can see that we're just generating some SVG XML. The less than that's XML operator, and it's the SVG is the tag, and then all of these are the attribute value pairs that go on that tag. And it's the same for we could see we're generating the defs, and then here's where we're putting in the we have two gradients actually. One is for the background, and we calculated the colors up above, and then there's another gradient for the face. I think this one's a pretty subtle gradient, but we just added a little bit. It looked a little bit better. So that's put in in a defs def section inside SVG. If you're familiar with SVG, you've probably run into that. And then the rest of this is the same thing. We're just generating line 62 is a rec statement. And then we're using line 65. We defined this ELP function above, and one of the first few lines it generates an ellipse. So we just had a shortcut function for doing that. And this is where we're just generating the eyes and the iris and everything that we calculated above. And then line 68 and 69 are adding the big paths that we have, and you could see that at the end of these 68 and 69 there's the M and the P. Those were the path strings that we calculated in the Fyrd functions, the Fyrd programs. So then at the end of this, we're setting some of the JSON properties that you can set for the metadata. And there's also another operator which I'll add in another video. I'm kind of running out of time here already, but it's a greater than and then an @ sign, and that's to set the attributes or properties that you'll see for the individual NFTs. And you can set 40 of those. So like we should actually have one set for the only one that we really would set here right now is for the hue, which is really it's the base color that we use, and so we should set that here. But yeah, I'll do that one in another video. So because I'm running out of time here. I don't want to have to make another one for the YEPs, but yeah. So that should give you a pretty good idea of how Gyve and Fyrd work together, and this is a good example of an on-chain NFT. So as far as customization goes, like I said, the colors would be probably something that you could customize very easily. You might, after line 69, we don't have a mouth, and we're only adding some hair and some eyes basically in the face shape and background. So that's something that you might want to add, and but you can have a lot of fun playing around with this Gyve script to customize your NFT to really look however you want. So I think that's I'm going to end the video. I'm up about 15 minutes. So thanks for watching.